There are these invisible forces all around us, constantly shaping our world. They're in the very air we breathe. They drive our weather, and they power so much of our technology. So today, we're going to pull back the curtain on this hidden world and really get into the rules that make gases do what they do.
Okay, so what does connect a deep-sea diver, a hot air balloon, and an exploding can of soda? I know, it sounds like the setup for a really weird joke, right? But the answer, it's not a punchline. It's actually this really elegant set of physical laws that explains all three. And to get it, let's start with the most high-stakes example of them all.
All right, so let's dive in. Literally, we're going deep underwater, a place where physics isn't just some abstract idea in a textbook. Down there, it is the thing that separates a good day from a very, very bad one.
I mean, the ocean is just this beautiful, mesmerizing place, right? But it's also incredibly unforgiving. It's an environment of just immense pressure. And that pressure dictates everything for a diver. Every single move, every single breath they take. It's all governed by that powerful, invisible force.
And the scale of this change, it's honestly mind-blowing. Right now, at sea level, you're experiencing about 1 atmosphere of pressure. But go down just 200 feet, that pressure jumps to over 7 times that. Just try to imagine that. It's like having the weight of 7 atmospheres all pushing down on you at once.
So you gotta ask, how on earth do divers survive that? How can you even breathe with that much force crushing in? Well, the secret is all about understanding how the air in their tank and in their lungs reacts. And it really all boils down to 2 surprisingly simple rules.
Okay, let's meet the 2 stars of the show, Boyle's Law and Charles' Law. Seriously, these 2 principles are the foundation for understanding pretty much everything about how gases work, whether you're at the bottom of the ocean or way up at the edge of space.
So first up, we've got Boyle's Law. Now, it describes something called an inversely proportional relationship. And that's just a fancy way of saying it's like a seesaw, right? As one side goes up, the other absolutely has to go down. So, if you keep the temperature steady and you squeeze a gas, decrease its volume, the pressure has to go up. And if you give it more space to expand, the pressure drops. Simple as that.
This is a perfect way to see it. Just look at this diagram. On the left, you've got your container, right? It has a certain amount of space, its volume, and a certain pressure. But now, watch what happens when we push down on that piston and double the pressure. Boom! The volume gets cut exactly in half. It's a perfect seesaw.
Okay, so our second star is Charles' Law. And if Boyle's Law is a seesaw, this one's more like a dance partner. It's directly proportional, which means the 2 things move together, in sync. Keep the pressure the same, you heat up a gas, and its volume gets bigger. You cool that same gas down, and its volume shrinks. They follow each other perfectly.
And here we see Charles' Law doing its thing. You add heat, right? The little gas particles inside get all energized and start moving around more. They spread out, and that pushes the piston up, making the volume bigger. This, by the way, is exactly how a hot air balloon works. You heat the air inside, it expands, becomes less dense than the cool air outside, and up you go. Now, these laws are so elegant, but they didn't just pop into existence. Nope, they were figured out over centuries by some really curious and brilliant people. So let's take a quick detour and meet the minds who actually put these pieces together.
The story really kicks off back in the 1600s when the barometer was invented. For the first time, we could actually measure pressure, and that was huge. It opened the door for Robert Boyle to figure out his famous law. But then, it took more than 100 years for the next big piece to fall into place, when Jacques Charles, who was a balloonist, started experimenting with temperature and volume.
And I think this next part is so cool, because it shows you how science isn't just one discovery, it's a ladder. Robert Boyle actually suspected there was a link between temperature and volume, but he couldn't prove it. And you know why? A good, reliable thermometer just didn't exist yet. The guy was literally a genius ahead of his time and his tools. Okay, so we've got the what, these really neat laws, and the who, the scientists who discovered them. But that story about Boyle being limited by his tools, that points to a much deeper question. The big one, why? Why do gases behave this way, so predictably? To answer that, we have to zoom in. I mean, way in. All right, get ready. This is the kinetic molecular theory. This is it. This is the microscopic why that explains everything we've just talked about. It's the secret engine running the whole show.
Okay, so here's the big idea in a nutshell. I want you to picture a gas not as, well, air, but as a giant swarm of tiny, tiny particles. They're all in this constant, chaotic motion.
just zipping around randomly inside their container, bouncing off each other, smacking into the walls. And here's the kicker. The average energy they have, basically how fast they're all moving, that's what we experience as temperature.
These images really help paint a picture of this beautiful chaos. Look at the left. You see the whole swarm in action. And then on the right, you can see the crazy zigzag path of just one of those molecules. It's like a pinball machine with trillions of balls all moving at insane speeds.
And this is where it all clicks into place. You ready? That thing we call pressure, it's not some weird abstract force. It's literally just the combined effect of all those trillions of particles constantly smacking into the walls of the container. That's it. More particles hitting the wall or hitting it harder and faster, that's higher pressure. It's this incredible idea that the chaos of the super, super small creates these perfectly predictable forces in our world.
So, okay, we've got the what, the who, and now the deep why. Let's bring it all back to our world, because I promise you, once you get this, you are going to start seeing these laws in action absolutely everywhere.
Just think about breathing. Something you're doing right now without even thinking about it. You probably think you suck air in, but you don't. What you're actually doing is using your diaphragm to make your lungs bigger. You increase the volume. And what does Boyle's law tell us? Bigger volume means lower pressure. So you create this little low pressure zone inside you, and the higher pressure air from the outside just rushes in to fill the gap. You are right now a walking, talking physics experiment.
And the examples just keep coming. That hot air balloon? Pure Charles' law. An aerosol can? That's all Boyle's law. Heck, the entire planet's weather system, it's just giant pockets of air heating up, expanding, and rising, or cooling down, contracting, and sinking. It's all just gas laws on a massive scale.
So, there you have it. From the incredible pressure at the bottom of the ocean to something as simple as taking a breath, these invisible rules are shaping our world every single second. It's a great reminder that underneath all the chaos, there's this hidden, beautiful order. Which just leaves one question, right? What other invisible rules are out there, just waiting for us to find them?